Hello students, welcome back. Previously we went through some examples of implicit relations and implicit curves, such as this, an ellipse, and this, a hyperbola, and something like this, an example of a Descartes volume. Moreover, we went through the concept of parametrization. Let's have a visualization again. Let's activate this cell and run the code. Okay, we are ready. So what do you see? We are looking at a moving dot model. Consider the red dot as the tip of the marker running through a whiteboard. And then after running through, what's left is a curve. And that curve has to be the implicit curve that we started with. If that's possible with some x of t and y of t, those are called the parametrization of this curve. And this expression is called the parametric curve. We're not trying to find out that parametrization or the expression of those parametric curves. Let's suppose that those x of t and y of t exist. In that case, we can consider x of t and y of t as horizontal and vertical position of this red dot which is moving around, and t is the time. And as time changes, x coordinate and y coordinate, in other words, horizontal and vertical positions change, and we are going to get rates of changes. The rate of change horizontally, x prime, and vertical rate of change, y prime. And they're going to be related one way or the other because x and y are related by this relation, implicit equation. So how will those x prime and y prime be related to each other? Well, that's what we are up to. Finding that is the implicit differentiation. Okay, enough of those examples. Now let's go to a little bit simpler example. Oh, wait a minute, this is cubic. It looks more intimidating, but not really actually. Look at the curve. It's simpler. Okay, all right. I claim this is simpler. Okay, how about the computation? Is that really simpler than before? Okay, we're talking about the derivative, so let's take the derivative. Derivative of the first term, 3x squared. That goes. Derivative of x cubed is 3x squared. Okay, all right. And the derivative of x times y, oh my, what is it? You see, we're already in trouble. And this one looks okay to me. Already we are in trouble. We need some different technique. Well, the key technique here is to realize both x and y are actually functions, x of t and y of t respectively. In other words, this one here is a shorthand of this, x of t cubed, x of t times y of t, and y of t cubed, like this. More explicitly, what do you mean by x of t cubed? Literally like this, x of t to the third power. Not y of t to the third power, you see? Okay, all right. Now if I take the derivative, it'll become a little bit more, it'll become a little bit more understandable. Let's take the derivative of this. It's a composite function. So 3 comes out as coefficient. Inside never changes. And subtract 1 from the power. Good. And by the chain rule, we have to multiply the derivative of the inside. This one here, the derivative of the inside. That's coming from the chain rule. I don't need this dot. Next, we have a product of two functions, x of t times y of t. So it looks like this time we have product rule. The derivative of the first function times the second function plus first function times the derivative of the second function. So x prime y plus y, x prime y plus xy prime. Okay, and then the same thing again. 3 comes out as coefficient, nothing changes inside. Subtract from the power, but by the chain rule, we have to multiply the derivative of the inside. So, pay attention to the left-hand side. We apply the chain rule for this composite function, chain rule for this composite function, and the product rule for this product function. Now, how about the right-hand side? Well, right-hand side is not equal to 1. It's a common mistake. The derivative of 1 is not 10, excuse me. I meant to erase and write 0. The derivative of 1 is 0. Derivative of any constant is 0. So there goes the implicit differentiation, and that's how x prime and y prime are related. You see, x and y are related like this, and x prime and y prime are related like this, and along with same x and y as well. So we have the relation of 4 functions, x, y, and also x prime and y prime. And of course, this is too complicated, a lot of t's, so we usually abbreviate this one like this without those t's. So this one too, we abbreviate like this. Just 3x squared, and then times x prime. And then this one is x prime y times xy prime. And then 3y squared and just y prime. Okay, there you go. So this expression here and that expression are the same, just simpler. So without doing any kind of t, you can get this result. So in the end, what did it do? S cubed became 3x squared by taking the derivative, and by the chain rule, we got x prime. Y cubed became 3y squared, and then by chain rule, we got y prime. And in the middle, we have the product rule. Here we go. Oh, no, not that one. Down here. I don't need this any longer. This. So whenever we apply the derivative rule with respect to x, x prime pops out. And whenever we take the derivative by y, y prime pops out. And the reason? The chain rule. Let's continue the color coding. Now, this expression we just used is French expression introduced by Lagrange. Lagrange is the person, the mathematician, who introduced the prime notation for the derivative. Lagrange, by the way, was born in Italy, but he studied in France, and then he did all his professional work in France. So yes, we can call this French expression. Now this one down here is by Leibniz. It's German expression. So if you prefer the German notation, use dx dt and dy dt in place of x prime and y prime. If you prefer French expression, use x prime and y prime. Me personally, I prefer French expression, and so does Wolfram Mathematica. But our textbook author prefers the German notation. As a matter of fact, you have to know both. You have to know they are equivalent. So I'm going to mix those up. Now, what happened here? We got two equations, the original equation and the second equation. If you want German, if you want French, then this one and that one. We have two equations, and then we have 4 unknown variables. Not only xy, but also x prime and y prime. 4 unknown variables and just 2 equations? In general, we cannot solve it. But if 2 of them are given from the problem, then we have only 2 unknowns and 2 equations. We can solve it. How? Well, let's discuss how in the next video. It can be a little tricky because very, very typically these equations become nonlinear. So we have a system of nonlinear equations to solve, some quadratic, quartic, or something like those. So it can be a little bit tricky, so we'll discuss those in a separate video. For now, let's remember this: implicit relation and how to apply the implicit differentiation. Remember, whenever you apply a derivative rule to x, x prime pops out. Whenever you apply the derivative rule to y, then y prime pops out. The derivative rules include the chain rule, product rule, sometimes quotient rule, and so on and so forth. Let's come back and do some example problems.